98% of your body's mass doesn't come from the particles themselves, not from atoms alone, not from the tiny particles inside atoms. If you could somehow pull out every quark in your body, the actual fundamental building blocks, and weigh them on their own, they'd account for less than 2% of what you feel when you step on a scale. The rest? It comes from energy, from the violent, invisible tension of the fields holding those quarks together. In physics, energy and mass are the same thing. That's what E equals mc squared is actually saying. Most of your weight exists because of forces, not because of stuff. We've known this for decades. The theory is called quantum chromodynamics, QCD. It works. The math matches the measurements. But buried inside it is a question nobody has ever directly answered in a laboratory. Is that mass fixed? Is it always the same number, no matter where the particle happens to be? Or does it depend on the environment? That question sounds abstract. It really isn't. A team of physicists in Germany ran an experiment designed specifically to test it. They fired protons into carbon, and in the wreckage, a particle may have been born trapped inside the nucleus. Here's what you need to understand first, and it's worth the 2 minutes it takes. Inside every proton and neutron in every atom of your body, quarks are bound together by the strongest force in nature. The particles that carry that force are called gluons, and the quarks and gluons inside a proton are not sitting still. They are in constant, violent motion, colliding, splitting, recombining, a storm of quantum activity that never stops. That activity costs energy, and energy has mass. That's the E equals mc squared thing again. The seething chaos of the strong force field contributes most of the proton's weight. Most of what you are is made of motion, not matter. Now, the equations that describe all of this have a specific property, a symmetry, that exists under extreme conditions, like the temperatures that existed a fraction of a second after the Big Bang, but that breaks down at normal temperatures. When it breaks, mass appears. That's where the mass in your proton comes from. Not from the quarks themselves, but from this symmetry breaking. Here's the part that connects to the experiment. Theory predicts that inside dense nuclear matter, inside a nucleus, where quarks and gluons are packed far more tightly than in open space, the conditions partially restore that broken symmetry. And if that happens, the mass of certain particles should drop. Not a little, by a significant fraction. The particle that makes this testable is called the eta-prime meson. A meson is just a quark paired with an antiquark, bound together. The eta-prime is a specific one, electrically neutral, no charge at all, and heavy, almost as massive as a proton. What makes it stand out is that its mass is directly tied to the symmetry mechanism we just talked about. It's essentially a particle whose weight is a direct readout of how that symmetry is broken. Change the symmetry, and the mass changes with it. Theorists have been predicting since the 1990s that inside a nucleus, the eta-prime should lose a substantial fraction of its mass. Nobody had ever tested this directly. Because the eta-prime is brutally unstable. It lives for a ridiculous fraction of a second before it decays. You cannot hold one still. You cannot observe it at rest. What you can do, in principle, is create one inside a nucleus and see if the strong force grabs it before it can escape. That's the experiment. At GSI, the Particle Physics Research Center in Darmstadt, Germany, a team accelerated protons to 2.5 billion electron volts and slammed them into a carbon target. The collisions produce eta-prime mesons. Most fly straight out. But if a meson is produced at just the right angle and energy, the strong force of the carbon nucleus can pull it back and hold it, briefly, as a bound system. The meson and the nucleus become a single object, an eta-prime mesic nucleus. Here's why the electric neutrality matters. Because the eta-prime has no charge, there's no electromagnetic attraction involved. Nothing like the force pulling an electron toward a nucleus. The only thing that could hold this meson inside is the strong force itself. If the bound state exists, it means the strong force is doing something inside dense nuclear matter that we can now actually measure. And what it seems to be doing is reducing the meson's mass. The detection setup, a combination called the FRS spectrometer and the WASA detector, looked for a specific signature in the data. When a particle gets absorbed into a nucleus instead of escaping, the energy of the outgoing particles doesn't add up. There's a gap, a chunk of energy that went into the nucleus and didn't come back out. That gap is the signal. They found it. Now, because this kind of result lives or dies on precision, the paper published in Physical Review Letters does not claim a confirmed detection. The team's own language is careful. The data indicates the possible formation of eta-prime mesic nuclei. Not proves, indicates. The signal is real. The statistics are solid enough to take seriously. But the exact binding energy, how tightly the meson actually couples to the nucleus, isn't measured precisely enough yet to close the door on every alternative explanation. The team knows this. They're already planning the next round of experiments with better instruments and higher beam intensity. The goal is to nail down the binding energy, the decay width, and the full energy spectrum of this system. If the signal holds up under that scrutiny, it becomes something very different from what it is now. Right now, it's a strong lead. And the implications, if it holds, reach far beyond a laboratory in Germany. Neutron stars are the densest objects in the universe that aren't black holes. Their cores are nuclear matter, compressed to densities we cannot reproduce on Earth. If particle masses shift inside dense nuclear environments, the entire physics of neutron stars changes. Their structure, their stability. What happens when two of them merge in a collision so violent it warps space-time and sends gravitational waves across billions of light years? We are detecting those waves right now. The numbers we use to interpret them depend directly on understanding what happens to matter at extreme densities. This experiment is testing exactly that physics, in a carbon nucleus, with a meson that lives for less time than it takes light to cross a proton. A particle trapped inside a nucleus for a fraction of a second by nothing but the raw force that holds all matter together. And in that moment, the data suggests it weighed less than it did the moment it entered. The team at GSI is coming back with better instruments. We'll have sharper measurements in the next few years. But the first signal is there, and what it's saying is this. If this holds, mass isn't just what a particle is, it's where a particle is. There are a few books in the description that go much deeper into QCD and the strong force. And if you want to keep going right now, I've got 2 videos on the end screen that connect directly to what we covered today. Thanks for watching. See you in the next one.